Okay, so the audio's on. We're at a minute till, and let's let's wait around for another few seconds, and then we'll get going. How is it going, Buddy B? I actually don't know how you want me to pronounce your name, so feel free to correct me. I could call you 64, but I don't think you would like that. But I wouldn't know. Buddy B sounds good to me. All right, I didn't mean to rhyme that, but okay, so we're good. All right, so let's hope the camera works and everything, and let's move on to the paper. All right, so okay, um, so since you're here, would you like to see the solution to the toothpick problem? Or do you want to just move on to the meat of the presentation today? I guess you could say. Okay. Well, we had let's not knock over the camera. We had this kind of thing, um, and we had to take away, I believe, three toothpicks and leave four squares. Um, but why? What? Excuse me. Chairs making noises. Why be negative about it? Be positive about it. So there's 17 toothpicks in the problem, which you can count yourself. I hope you believe me on that. If you take away three toothpicks, you're left with 14 toothpicks, and you want to make four squares, which means there's two toothpicks that belong to two squares, or one toothpick that belongs to three squares, but that's not possible. Um, so what we can do is look for all the toothpicks that are shared here, and just pick two of them to share, and hope that the rest gives you, yeah, no toothpicks shared. So, um, just for convenience, I'm going to pick this one and this one to start out. There's actually two answers to this particular problem. Um, so if we share those toothpicks, we end up with this on one side, and we have to find another square that shares no toothpicks. So we have an answer here, and that's one way to go about it. So instead of saying we want to take away three toothpicks, we can say we want to share two toothpicks. So this is one of the answers. But let's say that's not the only answer. So let's say we picked this one to share. Now we have to pick another one to share that is quote unquote very different. Um, we can't pick this one because if we picked this square, we'd share another toothpick. So that's out. So it turns out that the only two solutions are this and this. And so, or well, there's like other rotations of it and flips and stuff like that. But basically, the only two solutions are this and this, and so there you go. The trick here is to be constructive and not negative, and so that's the answer to one of them. The other one was take away five toothpicks and leave three squares. So that is the same as saying you have not two, I can't read, 12 toothpicks, and we want to leave three squares. Well, that implies that none of the squares share a toothpick. So the only one that really makes sense is this design, or if you flip it upside down, it's this. But that's the only answer there. And so be constructive about it is the sort of gist to the answer. So that's that. So that's the solution to last week's puzzle. At the end of this week, I'll try to see if I can figure out another puzzle to give you guys. This is not my puzzle, but the cool thing about this is you can just I have no idea. You're the second person who's brought that up, and I really honestly have no idea if that's that would help. Um, uh, the fact that these things can be disjoint might be a problem, but I really don't know, to be honest. Yeah. So like these two are disjoint, and this box is disjoint from the other three. This one has three disjoint boxes, so it could be, but I'm really not sure. Um, yeah. Okay. So anyway, this is my solution to the problem. Is it too loud, guys? Oh, I agree. But when you're sharing toothpicks, that also gets to be problems, I think. Not sure. Not gonna say for sure, but it could be. It could be some. I mean, you could adapt something that's like the Euler characteristic formula to the problem at hand, maybe. I'm just saying there's some pitfalls, maybe. I wouldn't know. I wouldn't know. I'll just leave it at that. Okay, so this is one way to go about solving the problem. It's it's not a terrible way. It makes things pretty quick. Okay, the sound is good. All right, cool. All right, so today I have oh wow, whoops, I'm having a day. Today, oh, what happened to my notes? This is bad. Give me a second. Let me turn off the volume for about like 30 seconds and try to find something. Okay, back. We're good. All right. So, uh, we're doing coordinate or sort of like Cartesian proofs today. Um, it's gonna be a lot of stuff, a lot of stuff, a lot of geometry. And we're gonna try to do some of these proofs both ways. But all the proofs that I'm presenting today are generally easier using the coordinate geometry methods. So let's see. All right. So okay. So coordinate geometry, just really quickly, is you have your xy plane, and then you have points like this thing here. This point might be like x naught, y naught, and why not? Um, so back in geometry, uh, you used all these triangle theorems to prove really simple things, or they were complex proofs, but generally simple things about squares and rectangles and other not four dimensional, sorry, four-sided figures. Because guess what? Yeah, you want to start with the simple things like triangles and then work your way up to more sides. So okay, so let's just flip this guy over. Um, I may not even remember how to do the proof correctly the other way, but here goes. Okay, so let's say you have a square, good old friend square, and one of the first things you want to prove is that the diagonals, let's say, are the same length. So I want to prove these diagonals are the same length. I'm like, okay, not too bad. One way to do this is to notice that one diagonal looks like the hypotenuse of this right triangle, and the other diagonal is the hypotenuse of that right triangle. And we can use Pythagorean theorem to prove, well, not just Pythagorean theorem. We can actually technically use congruent triangles, but one way to do it is to use Pythagorean theorem to prove that this is a root 2 and this is a root 2, and we're done. And so there you go. Let's just do all the square ones first. Okay, so this one is the diagonals are the same length. Okay. Um, then diagonals are perpendicular. Actually, I think I'm going to skip over all the proofs, or most of the proofs, to using geometry, because I think that would be kind of repetitive and somewhat boring. Some of these proofs in geometry are really difficult, and so we're going to skip over them. Okay, So anyway, this particular proof we've done already. The diagonals are the same length. Okay, so how do we do this proof using coordinate geometry? Well, okay, we're going to put a point here. So we're going to take any square you want and rotate it and kind of move it, translate and rotate until one point is at the origin. So this is 0, 0. One point is up here. This is A0. Oops, sorry, 0A. That's already bad. One point here, which is A0, and one point here, which is AA. So the question here is, again, how do you prove that the diagonals are the same length? Well, okay. Again, we have distance formula. This distance ends up being a root 2. We have distance formula here, also being a root 2. Yeah, there you go. They are the same length. Okay, so that's the first thing for squares we want to kind of talk about. The next thing is that the diagonals bisect each other. Okay. Let's see. So one way to do that is to find the midpoint of these two and the midpoint of these two and show that they're the same point on the graph. So the midpoint of 0a and a0 is a over 2a over 2. The midpoint of 0, 0 and AA is again a over 2a over 2. So it turns out that this is the midpoint of both this one and this segment here, or this diagonal here. So sort of a nice proof. This also means because oh, did I say the same length? Yeah, the same length. Okay, so because these two are the same length and they bisect each other, that means that this and this and this and this are all the same length, which also means that this object, this four-sided figure, or this figure with 4 vertices, can be inscribed in a circle, because you just take the middle here, center, and then all these other points are the same distance away. So that's kind of a nice corollary to the same length and bisect each other properties. Okay, and then finally, let's say that we don't know that the diagonals are perpendicular. How do you show that? It's super easy. You do slope of this one and slope of the other one. The slope from 0, 0 to AA is 1. The slope from 0A to A0 is -1. And guess what? If two segments have slopes that are negative reciprocals of each other, then that means they're perpendicular. And that's all you really need to use to prove all that. So, again, this is a square. When we just proved 3 properties of it, perpendicular diagonals. I'm kind of trying to rush a bit, but to get to like the fun stuff, this is just kind of like, wouldn't it be nice if we could do geometry this way? Which we could, but you know, textbooks and Euclid's Elements. But anyway, equal length diagonals. And finally, diagonals bisect. And there you go. So all 3 of these we proved in, I don't know, under like 5 minutes. So that's kind of nice. Okay, so let's move on from squares now to rectangles. So rectangles have some of the properties of squares, but not all of them. And let's see, where should I put this? What did I put out? Okay. So let's draw a rectangle. Rectangle again. You can take the rectangle, rotate it, and translate it until one of the points is at the origin. So this is 0, 0. Oops. Let's not earthquake the thing. This point here is AB. Sorry, A0. This point up here is AB. And this point over here is 0B. And you can take any rectangle and transform it to position it in this way. That's what I claim. I don't want to prove that, but I think we can just sort of agree on that, hopefully. So again, we have some properties of rectangles we want to kind of talk about. By the way, there are some things in this presentation that I haven't done before, so I might struggle a bit later. But for right now, this is not too bad. So first, diagonals are the same length. Hey, okay, sure. 0, 0 to AB would be, the length is square root of a squared plus b squared. A0 to 0b, again, is equal to square root of a squared plus b squared. So yes, the diagonals are in fact the same length. Let's see if they bisect each other. So another way to say that is that the midpoints of these two segments are the same. This diagonal has a midpoint of a over 2, b over 2. This diagonal has the same type of thing. They both meet here, so they do in fact bisect each other. Okay. And as a corollary to that, the rectangle also can fit inside a circle. All 4 points will be on the circle all the time if it's a rectangle. And that is because they bisect each other, and all 4 of these are the same, so you allow this particular point here to be in the center of the circle, and then all these 4 points are equidistant. And there you go. Okay, so here's one that I haven't done before, so we'll hope it goes relatively smoothly. Next, we're going to talk about rhombuses, or rhombi, or something like that anyway. A rhombus. Okay, so this one's a little harder to formulate, but we're going to try. And I think I've got this down. We're going to take a rhombus, we're going to rotate it, translate it, until one point is at the origin, 0, 0. I want to do this point first. So this point, let's say, is AB. And now I have to put in this point and then this point. And so what I'm going to do is this is going to be, so the B is going to be the same because it's the same height. But, oops, I should have written the X part first. Okay. So the X part is A plus square root of A squared plus B squared. And the Y part is just B. And this part will be square root of A squared plus B squared and B. And I'm hoping this will actually work out. I am not actually sure, but hey, we'll find out. Okay, so let's see. What do we need to prove about this? Oh, the diagonals are perpendicular. Well, that's going to be fun. Oh, okay. So a rhombus is when all 4 sides are the same, but not necessarily the angles are the same. Like that. It's not a kite, which is another thing that I didn't actually try to do yet. Okay, cool, good. Okay, so we might actually just explore kites today, along with everything else. All right. Okay. Really? That looks like that looks like Los Angeles. But anyway, all right. All right. So yeah, the distance from here to here is square root of A squared plus B squared. The distance to all the other places are, and hopefully we're good here. Okay. So let's try the perpendicular part first. So yeah, let's see if these are perpendicular. They're supposed to be. All right. So I'm going to find the slope of that one and the slope of this one and hope they are negative reciprocals. So the slope of this one is not too bad. It is b over a plus square root of a squared plus b squared. The slope of this one... Ooh, oh, just kidding. This is a 0. I apologize. Sorry. So the slope of this one is... I want to say it's equal to b over a minus a squared plus b squared. And if these two things multiplied to -1, they are perpendicular. Or wait, let me just make sure. Yeah. So let's hope that works out. So When you multiply them together, you get b squared on top. You get a squared minus a squared plus b squared, which, hey, gets you -1. So these two slopes are, in fact, negative reciprocals, and they are perpendicular. So nice. That was nice to get it right the first time. Okay, so that's the first thing that we need. The second thing that rhombuses happen to have is that the diagonals bisect each other. So we're looking for the midpoint here between these 2 points and the midpoint here between these 2 points. Okay. Or on that segment. Okay, so here you get a plus square root of a squared plus b squared all over 2, b over 2. Okay, that's good. So that's between here. This is the midpoint between A and C. So this is AC. And then we're going to try to find the BD one. BD midpoint. Again, the y value is b over 2. That's nicely obvious. And the x value is, yeah, a plus square root of a squared plus b squared all over 2. And hey, it works out. Good stuff. Okay. I might be going a little faster than I need to, but there's always stuff to do, so we'll jam pack this one. All right, so that's that. Why am I? Oh, here we go. Second page of notes now. Okay, so that's squares and rectangles and rhombuses. Let's do parallelograms. All right. So parallelograms. Let's redraw the plane. Let's rotate and shift. So this is 0, 0. Parallelograms. So again, this is AB. And this over here is just, hold on. Okay, so this is going to be, let's see here, maybe C comma 0, and this one will be A plus C comma B. And there you have your general parallelogram, which is always good. Okay, I want to read your stuff here. Hold on a second. Square root of a squared plus b squared plus b. Okay. Okay. Yeah. So let's bring back the rhombus. Are you using dot product there? I'm confused. Sorry. What is going on? Let's see. Yeah. Okay. So I agree. Dot product would work too. I'm just using the fact that M1, M2 is equal to -1. So, yeah. So that's the same type of thing. All right. Cool. All right. Dot product. Nice. Okay. So, parallelograms. So the special thing about parallelograms is the diagonals bisect each other. Let's see if that's true in our particular picture. We want midpoint here. So midpoint here is A plus C over 2, B over 2. And the midpoint of the other one is, again, A plus C over 2, B over 2. And that's it. We're done. These are really, 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 really nice proofs. They require a little bit of algebra, but not much. Okay, so now here comes the more difficult, or at least messier part of the video or the stream. So let's just take a minute and breathe, because the math here might get a little bit complicated. All right, you ready for this, buddy? All right. I'm purposely drawing slowly just to like not use too much brain power. But anyway, we're going to triangles now. And I'm going to make this C0, and I'm just going to put a random point AB here. So we have a generic triangle. We can rotate it and shift it to one point at the origin and another point on the x-axis. And the last point, we have no idea where it is. This point could technically be over here or here or here. It could be in any quadrant. But the point is that, we have a general triangle. Okay. So the first part of this is not too bad. This is an old theorem. Well, anyway, so I'm going to try to find the median here. Or I'm going to connect the midpoints of these two sides and connect them. Sorry. Yeah, so I'm going to find the midpoints of these two sides of the triangle, and I'm going to connect them. And there's a few things we can say about this. The first thing is that, let's just call it, well, not ABC, because we have plenty of ABCs. RST. Okay, and we'll call this D and E. And the first thing that you might know is that DE, when you connect these when you connect the midpoints, is always parallel to the base. Always. The second thing that we're going to prove here is that the distance here, or the length of DE, is always half of the length of RT. So let's see if we can do this. Let's try. Okay. And after this, we're going to try to do something really complicated, but hopefully it'll work out. All right. So yeah, let's find the coordinates of D, which is just D, A over 2, B over 2. And E is A plus C over 2, B over 2. Now, this is a super easy proof for parallelism because the bottom one is obviously parallel to the x-axis. DE has the same y value, so it's also parallel to the x-axis. So that part's super simple. The length part isn't too bad, hopefully. So the length of RT is actually just C. And let's see what the length of DE is. So D will be A plus C over 2 minus A over 2 squared plus B over 2 minus B over 2. Actually, you know what? I don't know why I'm doing this because they're horizontal. But okay, we use the distance formula. But anyway, we get what did I do? Oh, we get C over 2. Yeah, so works out. Good stuff. We're good. Again, these two are on the same y value, so we can just subtract the x's. So it would be C over 2 anyway, but hey, we did it the complicated way. All right, so that's that. Here comes the possibly very difficult part. I haven't actually done this like regularly, and if I I should have made notes, but it's Twitch, so kind of fun to try to wing it a bit. And we've got an audience here, so with the audience, we should be able to crack this one. Okay, so I am going to go for concurrent medians first. Okay, so median here, this will be AB, this will be C0, this will be 0, 0. Okay, what is the easiest way to do this? Yeah, okay. Let's just find all the midpoints first. This is C over 2, 0. This one is A plus C over 2, B over 2. This one is A over 2, B over 2. Okay, so we got all that. Wow, I don't know if you guys can even see that. I should write like bigger. Anyway, okay. So if I remember correctly, which I might not remember correctly, there's a concurrency proof where the point of concurrency is always 2/3 away from the point of the triangle and 1/3 away from the other point on the triangle. And I want to say it's medians, but I don't actually know. So let's just try it, and just because, like, why not? It's a super simple check, and if it's right, we're just done. And if it's not, then we got to intersect like 3 lines or something. It's no fun. So, yeah. So, this will be fun. Yeah. Okay. So anyway, the distance from here to here is a over c over 2 b. Okay, yeah. I need to divide by 3 and multiply by 2. Yeah, okay. So what I'm basically trying to say is we have a triangle, and this point and the median here, I'm looking for the 1/3 point between these two. So this is 2x, and this is x. That is what I'm looking for. It shouldn't be bad, but who knows? So let's do it. So this one's the easiest one because the vector starts at 0, 0. So we know the vector is oh, I can't say vector here. Then we're not. Then we might not be doing geometry. But for simpleness' sake, let's just use vector. Okay, we're doing vector calculus. Sorry guys, we're gonna cheat a little bit here. But anyway, the vector distance between here and here is a plus c over 2, b over 2, and we want 2/3 of it, and then add it to the initial point, which is 0, 0. So that'll get us to the point a plus c over 3. Hold on. Yeah, okay. This is starting to confuse me. That's okay, though. All right. And b over 3. So I think this is the coordinate we want for 1/3 of the way from here to here. So something like this. Okay. Let's hope that's right. So now we're going to get the vector from this point to this point. Okay. So that's going to be a minus c over 2 b. Okay, so a minus c over 2 b is the vector. We want 2/3 of it, 2/3 of the length. So this will be 2a minus c divided by 3. 2b divided by 3. Oh, that's already not good. Oh, actually, maybe not. Okay. So this is 2/3 of the vector here, but we have to add it. Oh, why did I take 2/3? Okay, sorry. This is 2/3, this is 1/3. So let's use 1/3 instead. That would be better. Sorry about that. So we're going to take 1/3. A minus c. Oh dear. So this is 2a minus c over 6, I want to say. Yeah. And then b over 3. But we are coming up from this point, so we're going to add c over 2 to this thing. So this is the vector, but the point comes out of c over 2 over c over 2, 0. So, yeah. C over 2, so this will be 2a, and then plus c over 2. That's 3c over 6, so this is plus 2c over 6 b over 3. This is the point that we want. Is it the same as this point? In fact, it is. Okay, so we now know that this point here, this point here is on the way from here to here and on the way from here to here, and so we have just one more left to check. And for that, I'm going to use some more paper. We will hope this works out. So the last leg of the journey is from a over 2 b over 2 to c0. So let's find the vector here. We're going to use c0 minus a over 2 b over 2. So c over a over 2. And then 0 minus b over 2, negative b over 2. So here's the vector. That is the vector from here to here. We're going to take a third of it and add it to a over 2b over 2 and see if that also coincides with this. So hopefully this will work. So this is more like we had the answer and we're verifying it, but I think I've tried this before. You can actually intersect all three lines and end up in the same point. This is what we call verification, and I wouldn't call it cheating, but it's a verification. Anyway, so okay, so here's the vector, and we want to add to it the point a over 2, b over 2. Oh wait, no, we didn't take a third yet, so let's take a third. C over 3 minus a over 6, b over 6, but negative. Okay, and we're going to take this vector and add it to a over 2, b over 2. Anybody coming in right now is probably like, what is he doing? But let's add this to this point, and we get c over 3 plus a over 3 b over 3. Hey. So all three times we got the same thing. A over 3, c over 3, b over 3. Where'd it go here? Oh, this one. A over 3, c over 3, b over 3, and a over c over 3, a over 3, b over 3. So we got the whole thing. It actually works out. And I am very afraid to do the next one because I think the altitudes one is way more difficult in this particular realm. So let's just briefly talk about it and hope that the answer comes out quickly. Although honestly, it might take like it might take an hour to kind of iron out all the problems. So let's try altitudes. All right, this might hurt. Again, we take a regular triangle. Sorry, an arbitrary triangle, and we rotate and translate. Okay. Well, the easiest altitude is definitely this one. This will be a comma 0. Okay. Let's see. Is there a nicely tricky way to do this? Okay, well, you know what? I'm just going to graph lines. So the first line is definitely x equals a. This is the definitely will work, but might be super messy way. So x equals a. The next one is this. We have this. And we have this. So the slope here is b over a. So this is for x equals a is the first line. Line number 2. We're going to try to draw that line. So the slope for this line is negative a over b. That's the slope. And we have a point, which is c comma 0. So using point slope, we get x minus c over y equals negative a over b, which just looks horrendous. Okay, well, that's fine. All right, so we can plug in x equals a here and figure out what the y coordinate is. So this is the first line is the second line. We're going to intersect them and kind of see if we can get the point down, which is here. Okay. Okay. Wow, this is going to be messy. So it's going to be y equals b times c minus a over a. Wow. Yeah. Okay. So this is the y coordinate. We'll put a little star here. Here's the x coordinate. Star there. Wow. Now we gotta see if that other line intersects. Okay. Well, like it's possible, but it might take a bit. All right. So we're trying to find where this segment intersects the perpendicular here. Okay. So the perpendicular is the altitude is perpendicular to the segment. The segment has slope of b over a minus c. I'm gonna say. Sorry, no. The slope of the segment here is that. Let me just make sure. Yeah. Okay. So the slope of the line is equal to c minus a over b. Okay. Let me just check my work here. Okay. So this happens to be going through the origin, I think, or did I mess that up? No, that's fine. Yeah, it happens to go through the origin. So y equals slope times x. I want to say, and yeah, x equals a. So y equals a times c minus a over b. Okay, that is a slight problem. This is not. This might not be right. Hold on. Something is not quite right. Something is not quite right. Did I not do the reciprocal slope here? Maybe that's what happened. Hold on. So that's b over a is the slope. So it's negative a over b. Okay. Negative a over b. The point is c0. Okay. X minus c is b. Okay, yeah. What have I done wrong? Okay, so maybe I messed up here. Slope is b over 0. Oh, wait. No. Slope is... Slope is b minus 0 over a minus c. Okay, so the slope of the line has to be reciprocal inverse. Or sorry, negative reciprocal. That seems right. Okay. All right. Okay, something went wrong somewhere. Okay. What have I done wrong? Yowzers. Alright. Oh. Wait, no? That's right too. Huh. Is it possible that this equals this? That would mean that A over B equals B over A. I must have messed up somewhere. Something is amiss. C minus A over B. Okay, well, if I don't get this in a few more minutes, I am going to defer to trying an example and, um, yeah, and hoping that the example works out nice. But for right now, let me keep thinking. Where have I gone wrong? This would be a good time to cue the Jeopardy music. I'm kidding. Let's see. Okay, so this checks. C0. Yeah, checks. Okay. So x minus c, y minus 0 equals negative a over b. I think that checks as the equation. Okay. A minus c over y, negative a over b. X is a, so yeah, that should check too. What am I doing wrong? Seems right. Can't possibly have messed up there. Uh-oh. So the slope of this line is negative. So that makes sense. It's b over a minus c. So the slope of the perpendicular is negative reciprocal. I want to say this is correct and this is correct. Negative run over rise. Looks good to me. That means that y equals c minus a divided by b times x. Y equals mx plus b, and b is 0. Or this b, but b is 0. Okay, what have I done wrong? I can't spend a lot of time on this. There's one more thing I want to do that is actually really interesting and a very short proof. Let's see. Y equals okay. Is it possible that a over b equals b over a? have I done? What have I done? Let's see. So we get this here and this here, and they're not the same. Huh. What have I done wrong? Oh. Okay, I'm an idiot. All right. This is not correct. It's like my slope formula is not correct. This is ridiculous. All right, so yeah, let's not do that. Let's do y over x minus c. Okay. Let's redo the whole thing with the notes we have already, and things will be good. Found it finally. I don't know my slope formula. All right, 0, 0. C comma 0. A comma B. Okay. So, this point here will be A comma 0. And the first equation is x equals A. The next equation I want to try to find is the one that goes through C0. So this is first equation, x equals A. We're done, because this is vertical. Okay, so the second equation, we want to find the altitude that goes through C0. The slope of that altitude will be negative A over B. And if I can remember my slope formula, y over x minus c equals negative A over B. All right, perfect. X equals A, though. So y equals negative A over B times A minus C. Okay, so that's the y value for the second line, as long as the x value for the first line is A. All right, so finally we have equation 3, where we're trying to find the perpendicular going through 0, 0. Okay, so the slope of that perpendicular line will be, altitude. Oh, did I say perpendicular? Altitude, right. We're trying to find the altitude that goes through 0, 0. It's perpendicular to this length here, so the slope of that line is going to be C minus A over B. All right, cool. Since it goes through the origin, the y-intercept is 0. We can write y equals C minus A over B times x. And because we can do that, we are pretty much done. X equals A. So we have here that y in particular is A times C minus A over B. And guess what? That matches this y here, and we are all done. That is the end of that. All right. Wow. Okay. So, know your slope formula. This is good. All right. So yeah, the first equation, or the first altitude, gives us x equals A. The second equation gives us the specific y value where where these two intersect. Okay, and this is the third equation. We want to prove it's all concurrent, that it all goes to the same point, and we get the same y value. So we're good. We're good here. I think that's all I want to say about that. All right. Yeah. So that's that. We're not going to do angle bisectors because angle bisectors are rather difficult when it comes to Cartesian stuff. So yeah. Okay. Portuguese, huh? Are you actually in a country that speaks that language right now? Okay, the last one is nice because we're going to do a calculus problem without any calculus at all. Nice. Brazil. Brazil's a nice place. Sort here. Pretty. And has some good places to go visit. Yeah. Okay. Sorry. All right. What is the derivative of this? So we have f of x equals square root of r squared minus x squared. And to find the derivative of this is what we call a Hassel. So how can we find the derivative without actually using any calculus at all? Well, I'll actually have two other things to say. This is the first thing. Okay. So yeah, so let's take a point here. This point here is x comma y. Actually, let's label it differently. A comma b. All right. So this point's a comma b. I want to figure out what the slope of the tangent line is there. You might notice that we have here a semicircle. So we can cheat by using geometry. What is the slope of the radius to that point? Well, oh dear. Sorry. The slope of the radius to the point is not hard to find because the circle, as I've drawn it, is centered at 0, 0. So the slope of the radius is equal to b over a. Yeah. Slope of the radius is b over a. And that means the perpendicular slope is equal to negative a over b. And there you go. So without too much craziness, a is the x value, so it would be negative x over square root of r squared minus x squared. Yeah, definitely. Wait, no, it's just AB, I think, right? Not negative B? Oh, tangential vector. Yeah. You're right. Okay. So yeah, so without any derivatives or anything too crazy, we can find, sorry, without too much calculation with the derivative formulas, you can just find the derivative. Okay, the last thing that I want to say is, okay, now you're just, my brain has turned to mush. All right, so let me just say the last thing I want to say, and then we'll see if there are any questions or comments or other things. All right, the last thing is this. This is a theorem that, like, I think almost everybody knows. There's a bunch of names for it. I don't actually know all the names. So anyway, but the theorem is, if you're given a circle, which that's a terrible one, draw a diameter, take any other point on the circle other than the ends of the diameter, connect the three, you get a right triangle. That's the theorem. It's not that hard to prove. In geometry, you basically connect this point here to the center. You have three radii that go to the circle, making two isosceles triangles, and then using some angle sort of addition and multiplication, you end up with the fact that this thing has to be a right angle. Okay, so that's nice. Decent amount of work, though. Let's try it with coordinate geometry. So, this point here again is x comma, x comma square root of r squared minus x squared. I mean, technically I can say all circles are similar, so we can make r1, but let's just leave it at that. So we're gonna show that this and this. Okay. Yeah. So we're gonna show that this angle here is a right angle. What we're gonna do is, this is kind of nice. First, this is the point negative r0. Oops, put too many parentheses. And let's see. This is the point r0. So what I'm going to do is just take the slope here and prove it's the negative reciprocal of the slope there. And that's it. That is the end of the story here. Let's try it. The slope will be square root of r squared minus x squared divided by x plus r. And the slope here is square root of r squared minus x squared divided by x minus r. And if I multiply these together and they become -1, that means they were perpendicular inverse. That means they were negative reciprocals. Wow. All right, so let's try this. R squared minus x squared over x squared minus r squared, and we get -1. And there you go. That is the end of the proof. Good stuff. All right. So a very slow recap, maybe. Let's see if I can find everything. 1 second. Okay, so really quickly, hopefully, we have paper after paper after paper after paper. Let's see. Part of that? Yeah. Okay. All right, let's go. Here we go. All the crazy stuff we did today. So we can start with this. We drew a rectangle. Oh, gosh. Okay. We drew a square. It was a square. I don't know what I'm talking about. We drew a square in the plane. We labeled some points as far as their coordinates. We found out that the distance formula here and the distance formula here is the same. So that means diagonals of a square have the same length. We found out the midpoint between opposite corners, and those were concurrent. The two midpoints happen to be the same, which also means that this is the halfway point between here and here, and it's also the halfway point between here and here, which also means that you can draw a square and draw a circle around it so that the circle contains all the points of the square. So 3 things, perpendicular diagonal. Oh, and we also did perpendicular diagonals, which means that this slope and this slope are negative reciprocals. And there you go. So that's the first thing we did. All right, let's move on to something else if I can find it. Let's do no. All right, so let's do rectangles. Rectangles. We have 0, 0, A0, 0B, and AB. Okay, cool. So again, we kind of talked about this. The midpoint here is this for both segments. The distance is the same. This is a squared plus b squared square rooted. This one is a squared plus b squared square rooted. I think that's all I want to say about that. Moved on to rhombuses. All right. Rhombi. All right, so I had the first point here. The next point was AB. This point was this distance moved to the right. So it was AB, but with extra stuff on the x value side, namely square root of a squared plus b squared. This point is just I almost said negative. This point is just square root of a squared plus b squared, square rooted, and 0. We proved that these two things are perpendicular by using slopes. We showed that, what else did we show? Anything else? Maybe that was it. Shuffle papers. Okay, I see. Okay. Alright, I can't find something, but that's okay. Next, parallelograms. So, super ridiculous synopsis here. We have a parallelogram, 0, 0, AB, A plus C, B, and C, 0. So, in a parallelogram, the two diagonals bisect each other. We found the midpoint of this one and the midpoint of that one, and yes, in fact, that worked out. And that's all I want to say about that. Okay, so then we had... Then we had some simpler triangle stuff. Oh, I see. Okay. I'll just redraw it, I guess, because I can't seem to find the paper. Yeah. So we had some triangle stuff where we had this generic triangle, found the midpoint of this, found the midpoint of this, connected these two. This segment is parallel to this segment, and then this distance and this distance are related, as in this distance is half of the other. Let's see, and I think that's all I want to say about that. We found out that the medians were concurrent, which I think I still have that one, hopefully. Yeah. We found out the medians were concurrent. We found out the altitudes were concurrent. We found out uh, a nice derivative formula that's super easy. And the final thing we did is the thing that went like this. We have a circle, and we take any point on the circle, we connect it to the ends of the diameter, and we find out that this is perpendicular. And that was a simple, we're going to take the slope here and the slope here, multiply them together, and find out that they're equal to -1, which means they are in fact, those two segments are in fact perpendicular. So there we go. Anything anyone wants to comment about? Because that was a lot of information. So yeah. I think if there are no questions, I am just going to call it a day. And that'll be the end of that. Geometry is fun. In this case, yes. I think the hardest, obviously one of the hardest, but there's some hard International Math Olympiad problems where geometry is more complicated. But yeah, this stuff is kind of a cool, like, just, hey, look, we can, calculate a few points on the plane. Oh, yeah. Geometry is usually not a university course. But anyway. Yeah, so. Yeah. So we have this stuff. Excuse me. Yeah. I think I actually took geometry in college, and it, it, it wasn't that bad, but I don't think the professor was trying to make it super hard either. So that was kind of the deal there. Um, in any case, thank you for coming, Buddy B. And yeah, for participating and chatting. I am grateful. And hope you learned something or got to see some proofs that have a different spin on the usual geometry stuff. And yeah, good stuff. Good stuff indeed. I actually have to go soon, but thank you very much for coming and yeah, participating. All right, see you later, guys. Hope you enjoyed the stream. I'll hopefully see you in a few days, maybe even tomorrow. We'll see. All right, thank you, and yeah, have a nice day. Good night.